Okay, I'm going to try this another time. The first time I had a mistake. I kept copying them wrong. Alright, maybe this time I'll get it right. So I think the thing that's most confusing about this is, first, the strangeness of the differential operator just makes it look different. And then it seems like there might not be any clear method to say, well, how do I know what to do next? And the answer is, there's lots of different ways to do it, so it's not like there's just one right way. And so if you're wondering, well, how did my instructor know to do this, that's the way they chose to do it. There could be other ways. Okay, so let's rewrite these. So keep in mind x and y are functions of t, so they're not variables, they're functions. So if we take the derivative of x, so that's the differential operator, so we're just rewriting this, dx equals minus y, and we can rewrite this one as dy equals x. Now I'm going to do this one, I think, a slightly different way than your solutions, just so that you can see there can be multiple ways of doing it. What we're trying to do is to combine these into one differential equation we can solve, and we might increase the order in order to do that. Or usually you don't want to increase the order of a differential equation, you want to decrease it. But if we're trying to simplify it, what is easier to solve? One second order differential equation with one function, or two first order differential equations with two functions. Probably easier to solve one second order with one function. So I'm going to get it all in terms of x. So I notice that this equation, and I just chose x, just not for any particular reason. Sometimes there's a good reason, like it'd be easier to do one than the other, but for this one I could do either x or y. And the way I see that is that the second equation has just an x in one place, and the first equation has just a dx. So that tells me if I take the derivative of the second equation, I can then substitute in for dx in the first one. And when I take the derivative of the second equation, I'm only going to get second order. I won't be introducing a third order or something weird. So I'll differentiate the second equation, and I get d squared y equals dx. And then I'm just going to do a substitution. So dx equals d squared y, so I'll substitute that in for dx. So d squared y equals minus y. Now I'll rewrite that in a way that looks more familiar. So I'll say y double prime equals minus y, or y double prime plus y. And now I have a perfectly good second order differential equation. It's not only good, it's homogeneous. It has the characteristic equation r squared plus 1 equals 0. This tells me that I have complex roots, and the complex roots give me a solution with trigonometric functions. So we have this, if I were to solve this, I would get r equals 0 plus or minus I. And so that's the solution. We don't have a real part, we just have an imaginary part, and the imaginary part has the coefficient of 1. So this tells me that x equals c1 sine of 1t plus c2 sine of 1t, cosine. If we had had a real part, we would have had an exponential part to this as well. Okay, now let's use our initial values. We have x of 0 equals 1. So that means x equals 1 and t equals 0. So the sine of 0 is 0, so that's 0. Cosine of 0 is 1, so 1 equals c2. So we know c2 equals 1. Well, we also know that dx equals minus y. Now, why did I choose this one? I need to find y, and I already have x. this equation wouldn't really help me much because I'm trying to find y. I'd have to integrate or something. This one is going to be a lot easier. So the derivative of x equals minus y. So minus y equals dx. So minus y equals the derivative of c1, which we don't know anything about c1 yet. c1 sine t, but we know c2 is 1, plus cosine t. So minus y equals, now I'll take the derivative of this. Derivative of sine is minus cosine, so minus c1 cosine t, plus derivative of cosine is minus sine t, or y equals c1 cosine t plus sine t. And we know that y of 0 equals 0. So y 0 equals c1 cosine 0 plus sine of 0, or 0 equals c1 plus 0, or c1 equals 0. Okay, so now we can go back, and we had that c1 equaled 0, and c2 equaled 1. So x equals cosine t, and y equals, so y equals c1 cosine t plus sine t, but c1 is 0. If c1 is 0, then y equals sine t. Let's see if that is right. X equals cosine t, y equals sine t. X equals cosine t, y equals sine t. Looks good. Alright, so let's check out this next one. Alright, so dx plus x minus y equals 0. 4x plus dy plus 5y equals 0. Now I noticed that he wrote this as follows. If you factor out the x, kind of weird to put it in front because that's just the differential operator works the other way. So dx, oops, d plus 1 times x equals y, or d plus 5 y equals negative 4x. And I noticed that was the way it was done on the solutions. Well, do I want to do it that way? I don't think I do, actually. I think yeah. I'm going to get this all in terms of x. And so what I'm going to do is I will replace y with d plus 1x. Okay, so what would this give us? D squared plus 6d plus 5 x equals negative 4x, or d squared x plus 6dx plus 5x equals negative 4x, or d squared x plus 6dx plus 9x equals 0, or x double prime plus 6x prime plus 9x equals 0. So then we get our characteristic equation, r squared plus 6r plus 9 equals 0, which factors into r plus 3 squared. And whenever you have a double root, that means that that gives us x equals e to the minus 3t, we'll put a constant in front, c1 e to the minus 3t, and that's one of them, and x2 is going to equal c2t e to the minus 3t. So that's how you do it whenever you have a double real root. And then we have we do not have any initial conditions, we don't, and so we have that d plus 1 x equals y. So if x is c1, so we can just say in general, so our most general solution is x is c1 e to the minus 3t plus c2 t e to the minus 3t. I'll go ahead and get the derivative of this. So dx is minus 3c1 e to the minus 3t. And then for this second one, I have to use the product rule. So the derivative of t is 1 times e to the minus 3t plus t, and the derivative of e to the minus 3t is negative 3 e to the minus 3t. So this gets me negative 3c1 e to the minus 3t plus c2 e to the minus 3t plus c2t negative minus 3t3 c2t e to the minus 3t. Did I finally get that right? Negative 3 c2t e to the minus 3t. And then minus 3 c1 e to the minus 3t and c2 e to the minus 3t. Those are like terms. I can write that as e to the minus 3t times minus 3 c1 plus c2 minus 3 c2 t e to the minus 3t. That's dx. Now dy, or y, was dx plus x. So dx is this. So there's dx. And then x is right here. So y is dx plus x. So if I look at my terms that have an e to the minus 3t, e to the minus 3t, I have a minus 3c1 plus c2 is my coefficient for the first one, and plus c1 is my coefficient for the second one. And then I have minus 3 c2t e to the negative 3t and plus c2t e to the minus 3t. So that'll give me minus 2 c2t e to the minus 3t, or y equals e to the minus 3t times negative 2 c1 plus c2 minus 2 c2 t e to the minus 3t. That's too many things for me not to have made a mistake, but so this was x. Now let's see if that matches. C1e to the minus 3t, C2te to the minus 3t. That's right. And then minus 2c1 plus c2, minus 2c1 plus c2, holy cow, minus 2c2t, minus 2c, I think I actually got it right. Okay, so there are those. Alright, now moving on to the next one. Dx dt plus y equals t. So dx plus y equals t, x plus dy equals 1. Alright, so how about we get let's see, so y equals minus dx plus t, and x equals 1 minus dy. I see what I want to do. So having done that, I see that this one is nicer. So if I take the derivative of x, my 1 goes away, and I get minus d squared y. So that means that dx is minus d squared y. So y, but then I have a t left over here. I don't like that very much. Let's see, so this is y equals positive d squared y plus t, so that's not homogeneous. Alright, so I don't like that. So let me try again. How about I figure out what dy is? So d squared x plus dy equals 1, or dy equals 1 minus d squared x. Oh, that's nicer. Why is that nicer? Well, we'll see why. So x plus 1 minus d squared x equals 1. Now if I subtract 1 from both sides, x squared minus d squared x equals 0. I have a homogeneous equation. I don't know why I said x squared. Or multiply through by negative 1, d squared x minus x equals 0. That gets me r squared minus 1 equals 0, or r equals plus or minus 1, which gives me x1 equals c1 e to the t, and x2 equals c2 e to the minus t, or x equals c1 e to the t plus c2 e to the minus t. So y equals t minus dx, dx equals c1 e to the t minus c2 e to the minus t. So y equals t minus c1 e to the t minus c2 e to the minus t, or y equals t minus c1 e to the t plus c2 e to the minus t, and x equals c1 e to the t plus c2 e to the minus t. Let's see if those work. C1 e to the t, c2 e to the minus t, and minus c1 e to the t, minus c1 e to the t, plus c2 e to the minus t, plus t, plus t. Yay! Okay, there we go. I hope that helps.